Okay, if you need a hint, feel free to look, but maybe don't if you don't need the hint. Okay, I'll talk through the logic in just a second, but I'm going to go ahead and calculate it for those of you that are almost there and just want to check. Did anybody else get that? I'm double checking because that doesn't sound familiar from last class for some reason. That's still what I'm getting. All right, so let's talk through the logic of it. Make sure we're comfortable with this. So starting from the reaction that we're trying to get to, okay, we want to make sure we get each of those chemicals and then make sure everything else cancels out. All right, so although this one initially seems a little bit weird, I'm always going to give you the reactions you need and not give you ones you don't need. So you're going to use all the reactions. You're going to need all of them, and you aren't going to need others. So in that respect, you can kind of be reassured that you're doing the right thing. Okay, so how do I get 1 mole of CuO? This is the only place where I have CuO, but it has 2 moles, and it's not on the correct side. So I need to flip the reaction around, which is why I wrote the negative on the side there by the delta H. So I need to flip it around, and I only want 1 mole, so I need to divide it by 2. So I have 1 mole of CuO, which is what I was aiming for. So that, this is what matches up. That's the thing I want to keep. And then I get a 1/2 mole of this guy on the product side and 1/4 of the O2. That seems weird. There's nothing wrong with it when you're just doing the math. It's not like a problem. Just make sure you're, okay with, I'm going to divide by 2 instead of multiply by 2 or whatever the case is. Okay, next one, CO. The only place I have that is in this reaction here. It's on the correct side, but I have 2 moles of it. I only need 1. So I'm just going to divide that reaction by 2 and get, I did that in my last class. That's bizarre. I forgot the O2 on that one. Okay, so I get 1 mole of CO, 1/2 mole of O2, 1 mole of CO2. Good, so I've got the thing I'm looking for. Next species in the reaction that I'm going for, next chemical, copper on the product side. Again, just 1 mole. This is where I have it in one of those reactions, but there's 4 moles of it, and it's on the wrong side. So flip it around, and if you want to do this in 2 steps, that's fine. You can always be like, did I do it right? Well, if you get the same number as I did, then you did it right, assuming I got the same number. I don't know why that's bugging me. It just doesn't feel like that's what I got an hour ago. All right, so flip it around and divide by 4. You can do that in 1 or 2 steps. So 1 mole, sorry, 1/2 mole of this, 1 mole of that, 1/4 of that. These ones are now on the products, that's on the reactants. So then I got my copper. Okay, and then last thing is the CO2. Okay, so I look in my reactions and I'm like, oh, the CO2 is in this reaction. I already used that reaction. And if I look, I got my 1 mole without even trying. So like you guys know, that very often happens where you either get something that you were looking for without making a concerted effort, or also in this case, you're ending up getting rid of things without intentionally doing it. So when we go to sum these up, you can see these guys are going to cancel out. They have to be on opposite sides of the arrow. That's why I lined the arrows up, was to remind you that if they're on opposite sides, that's when they're canceling. So these guys cancel, and then you've got a 1/2 here and a 1/2 there. Okay, so it's like that cancels with those. So this cancels with that, and that cancels with those 2. And so then you're left with everything that you wanted and nothing that you don't want. CuO plus CO, CO2, and Cu. So I'll leave that up there for a second. I have one other one we can do if we have time at the end. Any questions you guys want to ask on that one? Okay, the stuff we have to do today is based off of Hess's law, but it is actually a lot more simple because we're going to use very formulaic reactions, and that means we get to use an equation, which I know you guys love if you can just plug numbers in. So that's where we're headed today. So first thing to note is that stuff I skipped over, the stuff, we're not going to do it. I just checked. It's not even in the homework. The reason I like to do it is because it's in a lab, but it's a lab from last semester, so it's kind of a little late anyway. But it's a good reminder because this is the chapter where we do that. It's an experimental way to determine enthalpies, and all the others we're doing are calculations, so that's another reason why I like it. But we make a lot of Why can I not think of that word this morning? I keep wanting to say exceptions, and that's not what I'm saying. I feel like my brain is a little kaput. All right. There's a lot of exceptions, adjustments we make to make this work. And so it's not super accurate. So anyway, we're going to skip that. We're not going to do any problems on that. Okay. So like I said, we are going to apply Hess's law to a new way to solve enthalpies. And it's going to be using these very specific type of reactions called standard enthalpies of formation. So standard implies what the conditions are at. So that's the first thing you need to know as part of this. So this is not STP like in gases, because that was 0 degrees Celsius. And standard states when we're talking about enthalpy are more like room temperature, so 25 degrees Celsius. If there are any gases, they're going to be at 1 atmosphere. And if there's any solutions, they're going to be 1 mole per liter. So that's the conditions. That's where standard comes from. That's also what this little, looks like a degree sign. It's a naught. That's what is implying standard conditions. When you see that little circle, that's what it's telling you is this is a 25 degrees C and 1 atmosphere of pressure, et cetera, et cetera. Okay, so then the second thing you need to know about this is what do we mean by formation? So this is going to be a table of values for any given chemical to form 1 mole of it from its elements. So for example, just show you one of those at the bottom here. So, for example, if I want to form 1 mole of CO2, or rather, if I want to know what reaction, let me show you what it looks like in the tables first. Oh, there's a good example right there. Okay, so when you look these up in like a textbook or a set of values online, it's going to give you the compound and it's going to tell you delta H, and see that little F at the bottom? That's formation. Delta H of formation is this value. So usually when we see delta H's, they have a reaction associated with them. These ones don't. They just have the compound. That's because the reaction is a very standard definition, and so they don't have to tell us what the reaction is because it's implied by the fact that it's a formation reaction. So when it says that this value for CO2 is negative 393.5, what it is implying is that it takes that much, or releases rather, that much energy to form 1 mole of CO2 from its elements. So whatever thing is in the table, we're going to make 1 mole of that on the product side, and we're going to start from its elements. So carbon and oxygen, but don't forget oxygen comes in pairs. So remember the diatomics, there's 7 of them: hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, iodine. So if those are their elemental form, that's how they're going to start on this side. If it was like iron, it would just be Fe. If it was selenium, it would just be Se. But when you've got something that's diatomic, it needs to come in its pair. All right? So the reaction that corresponds to the delta H of formation of CO2 is carbon plus O2. So before we scroll down and show you more examples, let's just do some of those examples that I know are coming. Okay, so water. Elements that go into making water, hydrogen and oxygen. But both of those are diatomic. And for this reaction, we only want to form 1 mole of the water. So how do I get 1 mole of water from 2 hydrogens and 2 oxygens, I have to put a half in front of the O2. This is one of the rare times when we will use and this is why you've seen not whole number coefficients in like examples that we've done already, is because when we do these kind of manipulations, it's very common for us to bend the rules a bit because we're not using exact real balanced equations that are actually happening. We're just kind of manipulating the math. Okay, so you do whatever you need to the reactant side to make sure there's 1 mole. Let's do another example. I'll let you guys do this one. Actually, let's do C2H5OH. Okay, so if I look up this value, in fact, I'll go look it up and write it down there. Negative 277.6. So the delta H of formation, negative 277, I think I said 0.6. Okay, so when you look it up in a table, that's all that's going to be written. And I want you to write down what reaction does that correspond to, that delta H. What reaction is it talking about? There they go again. Every class, it's like the instructor gets tired of talking and is like, let's watch a video for a half an hour. I'm so rude. Watch, it's going to be like somebody from my department. And
We only did videos in my classes. I think we're very going to get shut down. We'll just find a video on YouTube.
I know. And then would you actually do it, though? That's the problem.
Yeah, that is a problem.
Okay, so we need 2 carbons. Elemental form of carbon is just carbon. 6 hydrogens, so 3 H2s, and then still just 1 oxygen, so a half O2. So you always just keep 1 mole of the thing on the product side and then do whatever you need to on the reactant side to get the right number of atoms. It's like balancing, but it's a lot easier. Okay, so when you look at those tables, this is what reactions they're talking about, is starting from the elements. So I do want you to know that, but the thing that's really cool about this is that in the end, you don't actually have to write down the reactions. So I'm going to show you the equation, and we're going to do it using the equation, one of these Hess's law type problems. And then I'm going to show you why it works the way it does. Okay? There's a couple more examples if you need them. Okay, so here's the equation. This is to find a delta H value for some reaction. So just like we did before, let's say like this is our goal reaction. We're trying to find the delta H for this. And instead of having a bunch of equations that we have to manipulate, we are going to use the delta H of formation values. So in reality, in the rest of this page, it'll show you how this works out with Hess's law if you actually used the equations, but we're just going to skip over the equations for now and use this mathematical equation rather than a chemical equation to calculate the delta H. So that's a summation sign. We talked about this at some point. We were like, what's a capital sigma? There we go. There's our capital sigma, okay? The N is going to be whatever the coefficients are. Oh, and I noticed this in my class. Somehow this one didn't get balanced properly. There should be a 2 in front of that water. So when we do this for water, we want to multiply it by 2. So we are going to take the delta H of formations of the products, multiply them by their coefficients, and add them all together. So the CO2 and the water. And then we're going to subtract the CH4 delta H of formation times its coefficient, the oxygen times its coefficient, and we're going to take the products ones and the reactants, subtract them. And that will give us the delta H for this reaction. Okay, so products first. So delta H of formation of CO2, and the coefficient's just 1. So I'm going to say 1, but 1 times that plus 2 times the delta H of formation of H2O. So that's our products. Minus our reactants, delta H of formation of CH4 plus 2 times the delta H of formation of O2. Okay, so CO2, we're going to go look these values up. So if you scroll down quite a bit further, there's these 3 pages worth of values. This is how they appear in any like table or anything. So what did I say? CH4 or H2O? CO2? Whatever. Okay, let's just grab one of them. CH4? Okay, good. But that was one of the reactants. Shouldn't products be first?
You said CO2.
Did I? Okay, good. Let's go with that. Okay, negative 393.5. Yeah, negative 393.5. Then I'm going to add 2 times whatever H2O is. I think is on the 3rd page here. Yep. Now this is an interesting point. There are actually different values, whether it's a gas or a water or a liquid in the reaction, because delta H is potential energy, and water and gas has different, I keep saying water, liquid water and gaseous water have different potential energies. I think in our equation it was gas, so negative 241.8. These are all in kilojoules. Oh my gosh, I think she is. I think that's a biology professor. It was just a clip this time, though. It wasn't the whole class.
She's like, I have next.
Yeah, right? She's a biology
She's
professor.
like,
Oh, that must not be who I thought it was then.
weird.
Yeah, okay. I can,
Doctor Costa
okay.
okay.
All right, now 1 times CH4, negative 74.6. Oops. And then 2 times O2. Why is it 0? Oxygen's already in its elemental form. So anytime you have something that's already in its elemental form and you're forming it, there's no change. So you don't even have to look those up. Like if I gave you a list instead of a table, maybe I just wouldn't give it for oxygen. And I'm sure somebody would be like, I think you forgot to give us a piece of information. It'd be like, you have all the information you need. Is that a question, Lily? No. Okay.
It's itching.
Itching, that's not allowed.
Why not?
So like calcium, just plain old calcium, it's 0. So if it's already in its elemental form, it's 0. Okay, so 0. All right, so now we just solve it out. I want to say it's like 800 something.
Negative 951.7.
I think you did something wrong. Because it's on the next page, right? Yeah. Times 2 maybe in there?
There's a times 2 in there.
Negatives? The negatives are always a pain. Because it's like minus a negative. Did you maybe add? No, that wouldn't have done it. Anybody else get 802?
Tried those, yeah.
Okay. Sorry, Lily.
Hold on.
Okay,
Okay. I got it.
good.
I negative. Does
Negative,
it-
negatived.
A positive negative? I don't
I was
know.
going to say you were supposed to negative, so maybe you negative the first one.
Oh, no, I got it to work out.
Okay. All right, so the equation itself is on the exam equation sheet. You just need to know how to use it. Let's look at why it works out. This doesn't really matter. I'm going to skip that one because this is better showing it. It doesn't really matter why it works out because you're just going to use the equation anyway, but it's always nice to see it once. So we said products, so CO2 and water, okay? So if I want 1 mole, I forgot the 2 again in this one. They did it in the reaction, just not in the equation above. This might have been me. I take stuff from the book, but then I like change it, so it's possible it was my mistake. All right, so we need 1 mole of CO2 on the product side. So you take the delta H of formation, right? It's already on the product side, and it's already 1 mole. So we use it as is. So that's why in the equation, we just take that delta H value. For the water, we need 2 moles of water. So we take the delta H of formation, but then they multiplied it by 2. So they had O2, they had a half O2 and 1 H2. And then they multiplied it through by 2. They multiplied the value through by 2. That used to be like 241, I think. So that's how they got the water. Get rid of these highlights. So CO2 and H2O, 2 H2Os. Recognize that each of these equations they're using, though, it's like they looked up the delta H of formation value and then they wrote the corresponding equation. CH4, they had to flip that one, right? Because it's always to make 1 mole of CH4. So when they flipped it, they changed the sign. Well, look what we did. We subtracted it, which was changing the sign. It's the same thing. So ours became a positive 74.6. So did theirs because they flipped the equation around. So then they got 1 mole of CH4 and 1 mole of CH4. And then the O2, nothing happened there, so we didn't need to write that down. It would have just been a 0 value. So now let's look at what cancels out. Because these start from their elements, the stuff cancels out really easily because we had to have carbon to make CH4. We also had to have carbon to make CO2. So like this carbon on the product side cancels out with that carbon. I wish they would have lined up the arrows. This one I think was from the textbook. I wish they would have lined up the arrows so you make sure you see this is on the reactant side, that's on the product side. Okay, so those cancel. The H2s cancel, And then the O2s are what add up to give you the 2O2 in the reaction. So at first it seems like, whoa, that was like really creepy that it just worked out just fine. But it's just because you're always starting from the elements. So if you make one thing, you kind of like turn it into the elements, and then you take the elements and turn them back into the products you want. Okay? So this is why it's an application of Hess's law. You're not going to ever do it this way because you're just going to take the shortcut and use the equation. But that's why it works out, is you're just using Hess's law, but they're with very standardized equations. So I do still want you to know what it means when I say a delta H of formation. Like let's say I said, identify the correct reaction that corresponds to, the enthalpy of formation for sodium nitrate. Okay? I would want you to be able to select Na plus a half N2 plus 3/2 O2. Is that right? 6 divided by 2, yes. Okay, so recognizing what, and maybe I would have something else like, I don't know, 2 NaNO3 and 3 O2s and 2 NAs and an N2, right? So like that one is not correct because you only want to make 1 mole of NaNO3. Okay? So I want you to know what those are. You're not actually going to end up using them. It's just that's why using them in this equation works out. It's an application of Hess's law. All right, let's have you practice another one. So you're going to need to use those tables. And these should all be gases. I think I just cut off the states there. So go ahead and use those tables and calculate, using enthalpy of formation, calculate the enthalpy of this reaction. Okay, feel free not to look if you're doing just fine. So I'm not even gonna include oxygen there because that's 0. Think of it as final minus initial, products minus reactants. Anybody else get that?
Yes.
Okay. So I'm debating between which 2 examples we should do. I kind of think we should do another Hess's Law problem, but yeah.
On the one before this, why does it have a coefficient in front of H2O?
Because there should have been, it just wasn't balanced in the equation. So yeah, that was my fault at some point, but it was earlier on. So there should have been a 2 in front of the H2O. Yep. So I'm going to switch back over to those practice problems I had earlier. And we're going to use, just as more of like a standard Hess's Law problem. Oh, is that even the one? Yes, it is. Okay. So here is the goal reaction that we're looking to find the enthalpy for. And this one is pretty messy, but you might as well get good practice before you do the homework. It looks like there's only one on the homework that's like this, so I'm glad we're doing a bit more practice in class. Okay, so this is not delta H's of formation. This is known reactions that we're manipulating to find the delta H of an unknown reaction. Okay, so I've written down what I'm going to do with each of the reactions. This one's actually pretty straightforward, even though initially it looks kind of weird because you're going to have to use like a fraction of things. But it actually works out pretty cleanly.
You forgot the oxygen again.
Sheesh. That is weird. It's like some, I don't know. It's odd. I did it in my other class too, so it's not, it's like the third time this morning. So the only thing that I find weird about this one is making sure that I got rid of all of the F2O, because on the product side, you have 1.5, and then over here you have 3 halves. So just recognizing that those do cancel out is probably the only thing that's a little bit tricky. So you get your 1 CLF, your 1 F2, and your 1 CLF3. Again, you have to do divided by 2. All of these are divided by 2. It's just that one of them is then flipped. So half ClO2 cancels out. You're left with your, now wait, why, oh, there's the oxygen. The oxygens, these two cancel out with that one. And then these 2 F2Os cancel out with that one. Does anybody have the value?
I got -110.05.
-110.05. Anybody else want to second that? I'll plug it in real quick. I got 108, but I might have just plugged something in wrong. Okay, it's very close. You probably just punched one little number in wrong. It's close enough you would have picked the right answer. Okay, so homework tomorrow night and chapter 12 prep. Okay?
I'm gonna get the breakdowns out. Oh yeah, I did 164.7.
Oh, instead of 160. I figured it was something like that. So,
It's between and aspirations. That's just